think getting to Mars is the big final boss of space travel, but Jupiter makes Mars look small in a way that is hard to accept at first. Here is the basic fact. Jupiter is not just further out. It is in a different distance class. At its closest, the gap between Earth and Jupiter is about 588 million kilometers. On average, it is closer to 714 million kilometers. Those are not just big numbers, they mean this. Even at the best possible moment, you're still dealing with more than 500 million kilometers of empty space between you and the planet you're trying to reach. Now here is the part that really breaks your normal sense of speed. Even light, which is the fastest thing the universe allows, takes roughly 35 to 50 minutes to cross that gap, depending on where the two planets are in their orbits. So if a signal leaves Earth, by the time it reaches the spacecraft near Jupiter, you have waited well over half an hour. If you send a reply back, the full round trip is over an hour. That is how large this distance is. Even light feels slow. So when you imagine driving there, or sending a quick crewed mission the way you send cargo planes around Earth, you're already thinking in the wrong scale. You're off by orders of magnitude. And that leads to the next question. If the distance is that bad, can we at least solve it with raw speed? You might think, fine, it is far, so we just go faster, we build a more powerful rocket, we cut the travel time down, but the reality of our fastest missions is very sobering. Look at what we've already flown. Probes like Voyager, Galileo and Juno were not simple straight shots. They used careful gravity assists, flying past other planets to steal a bit of their orbital energy and pick up speed. They were designed from the start to squeeze every bit of performance from their trajectories. Even with all that, Galileo took about 6 years to get from Earth to Jupiter. Juno, launched decades later with modern engineering and a powerful rocket, still took around 5 years to arrive. And remember, these are small uncrewed spacecraft. No life support, no heavy shielding for humans, no huge reserves of food and water. Planned missions like Europa Clipper live in the same world, they also need multiple years just to reach the Jovian system. Even New Horizons, one of the fastest objects humans have ever launched from Earth, took more than a year to cross Jupiter's orbit on its way to Pluto, and that was a flyby. It did not slow down and stop, it just passed through. If you try to imagine something that can actually break and enter orbit around Jupiter, while also carrying a crew and everything they need, you're not cutting the time down, you're adding mass, and that usually makes trips slower, not faster. So then you might ask, if we accept long travel times, can we at least choose when to leave and when to come back? This is where orbital mechanics shuts the door again, because you cannot just decide to go whenever you feel like it. Earth and Jupiter both orbit the Sun at different distances and different speeds. To travel between them efficiently, you have to launch during a specific window, when their positions line up so that a transfer orbit is possible without wasting absurd amounts of fuel. These launch windows do not happen every week. They come around roughly every 13 months, so about once a year plus a bit. If you launch outside that window, your choices are bad. Either you burn a huge amount of extra propellant to brute force your way onto a workable path, or the trip becomes so long and inefficient that it is simply not worth doing. For a robot, that is an engineering and budget problem. For a human crew, it is a life problem. Your departure date is fixed by the sky, not by your training schedule. Your return options years later are also locked to these windows. If something delays your work out there, or a system failure pushes your timeline, you might miss the ideal return window and be forced to live with a longer, harsher trip home, or, in extreme cases, not have enough fuel to come back at all. So the next question is simple and brutal. What does that do to a human lifespan? With the propulsion we actually use now, and with realistic upgrades in the near future, you're not talking about a quick adventure, you are talking about a mission that eats a serious chunk of your life. Outbound cruise, even with good alignment, is years. Then you want time to actually do something at Jupiter, not just fly past. Then you have to wait for the right moment to head home, and then survive more years of flight back toward Earth. Add it all up, and a round trip can easily push toward a decade. Now think about what that decade looks like from inside the spacecraft. You're in a closed environment with a small crew in deep space for year after year. Every breath you take depends on hardware running correctly. Every litre of water has been filtered and recycled again and again. Every piece of equipment has to last or be repairable with the tools and spare parts you brought from Earth. There is no backup ship behind you, no station you can divert to, no fast rescue mission. If something goes very wrong in the outer solar system, the only realistic outcome is that you deal with it yourselves, or you do not survive. So distance is not just about how long the trip is, it is about how long you are forcing a tiny, fragile, human-made world to operate without any outside help. And that leads to the last big question for this first part. Maybe we could just scale up what worked for the Moon and what might work for Mars. Or is Jupiter's distance something qualitatively different? On paper, it is easy to fall into the trap, you say. We went 3 days to the Moon, we might go a few months to Mars, so we just go more months, we pack more stuff, and we get to Jupiter. But that is not how the problems grow. At Jupiter's distance, everything multiplies. Life support has to run for many years, not months. Radiation exposure builds the whole time, not just during a short cruise. You need more food, more water, more spares, more shielding, and every kilogram of all that has to be launched out of Earth's gravity well, accelerated across the solar system, and, if you want to bring people home, decelerated again. Psychologically too, you're pushing people into isolation and delay on a level we have never tested. Mars is already a huge leap in that sense, Jupiter is much worse. So when mission planners look at Jupiter as a human target, distance alone starts to look like a near showstopper. Before you even touch the issues of radiation, gravity, storms, or lack of a solid surface, the raw scale of the trip stretches everything we know how to do until it looks less like exploration and more like a one-way exile to deep space. And here is the kicker. Even if you somehow accept that, there is a deeper problem hiding underneath. Because in space, you cannot just point at Jupiter and fire your engines. If you try to fly straight to Jupiter, you don't just fail, you miss the entire planet by millions of kilometers. Because in space, pointing at where a planet is now is almost never where you need to go. You're not flying through empty space in a straight line. You are falling around the Sun in an orbit. And Jupiter is also falling around the Sun in a bigger, slower orbit. To get from Earth's path to Jupiter's path, you have to change your orbit in a very specific way, and that change has a cost. That cost is called delta V, which simply means change in velocity. It is not just how fast you go, it is how much you change your speed and direction compared to where you started. Every time you want to move to a higher orbit, farther from the Sun, you have to add more delta V, and the amount you need jumps quickly as you aim for the outer planets. The most efficient way we know to do this with normal rockets is something called a Hohmann transfer. Instead of going straight out, you hit the engines once near Earth to put the ship on an elongated path around the Sun, with the far end of that path touching Jupiter's orbit. Then, when you reach that far end, you fire the engines again to match speeds with Jupiter. It is like stepping from one moving walkway to another. You do not aim at where the other walkway is right now, you aim at where it will be when you arrive. That works well for fuel, but here is the catch. Every extra bit of delta V you want means you need more propellant. And for chemical rockets, propellant mass grows in a nasty way. The more fuel you load, the more fuel you need just to push that fuel, and the curve goes up steeply. By the time you push orbits all the way out to Jupiter, the delta V bill is huge, and the rocket equation is basically telling you, if you try to do this with a human-class ship, your propellant demands blow up. So then you ask, fine, if pure Hohmann transfers are heavy and slow, can we cheat with clever tricks? Can we use planets themselves to help us? Can gravity assist save us? This is where the story sounds smart on paper and ugly for humans in practice. A gravity assist is when you fly close behind or in front of a planet, letting its gravity bend your path and change your speed relative to the Sun. You steal or give a tiny bit of the planet's orbital energy, and you get a boost or a slowdown without burning as much fuel. Missions like Juno, Cassini, and many others did multiple gravity assists, swinging past Earth or Venus more than once, carefully stacking small changes into a big overall change in trajectory. For a robot, this is great. The spacecraft does not care if the trip takes a few extra years, it does not care about extra passes near the sun, it does not get bored, it does not get cancer. For a human crew, every extra loop is more time in deep space, more radiation exposure, more aging of hardware, more chances for something to break. There is another problem too. Gravity assist paths are tightly planned. Your flyby altitude, your angle, your timing, they all have to be incredibly precise. If something goes wrong early in the mission, your options to bail out are already locked by a chain of planned flybys years long. You're basically tying human survival to a pre-computed path with very little margin, and if you ask yourself honestly, would you put a crew in a vehicle where a tiny navigation error at Venus decides whether you make it back from Jupiter 10 years later? You start to see why this strategy is a lot more comfortable with robots than with people. But let's say you accept all that. You ride the gravity assists. You manage the Delta V. You reach Jupiter space. Are you done? Not even close, because flying past Jupiter is one thing. Stopping there is a different level of problem. By the time you reach Jupiter, you are moving very fast relative to the planet. To go into orbit, you have to get rid of a huge amount of that kinetic energy. There are only a few ways to do it. You can fire your engines for a long burn, slowing yourself enough for Jupiter's gravity to catch you into an orbit, or you can try risky options like using a moon or a bit of atmosphere to bleed speed, which is even worse for a crew. For current near-term ships, the realistic option is a big engine burn at exactly the right time. That orbit insertion burn is not a small tap. It is tens of minutes of continuous thrust at a very precise point in space with exact timing. If the engine underperforms, if a valve sticks, if guidance is off, you do not get a gentle second chance. You either end up in the wrong orbit, maybe skimming dangerous radiation zones, or more likely you do not get captured at all, and you fly past Jupiter on a path that sends you into deep space with almost no fuel left to do anything useful. For a robot, that is a failed or partially failed mission. For a human crew, that is a death sentence written in orbital mechanics. So you might think, okay, then we design good abort options, we build in safe escape paths the way we do near Earth, but that is where the distance crushes you again. Near Earth, and even with some Mars trajectories, you can design what are called abort modes. If something goes wrong at certain phases, you can cut short the mission, loop around the moon, or adjust your path to come back to Earth on a free return, or with a manageable extra burn. The energy differences are large but not insane, and the timings are days or months, not many years. At Jupiter distances, the energy scale is so big and the timing so tight that meaningful aborts are very hard to design. If you try to abort to Earth from a bad Jupiter approach or a damaged orbit, you still have to pay a massive Delta V bill to climb out of Jupiter's gravity influence and shape a new path back towards the inner solar system. That means you would need to carry a lot of extra fuel that you might never use, which makes the entire mission heavier and harder from the start. And even if you do pay it, that return path is not quick. You are still talking years. So in practice, abort often means this. You give up on your original science goals and accept a crippled trajectory that wanders home late, with a crew that has spent even more time in deep space than planned, maybe with damaged systems, maybe low on supplies. In the worst case, there is no real abort at all. There is mission lost and nothing you can do. That is the kind of risk profile that makes real space agencies step back and say, maybe we do not send people into this situation at all. And this is where the cold math of orbital mechanics quietly makes the decision for you. Every tool we know how to use to reach Jupiter, Hohmann transfers, gravity assists, large insertion burns, all of them are fine for metal and silicon. A probe does not care that the flight takes 6 years. It does not complain that it cannot turn around and come home. It can sit in a radiation belt until it fails, and that is acceptable. But humans are different. You need constant life support, you need food, you need a path home that is not pure fantasy, you need some margin for error. When you mix those human needs with the reality of how you actually get to Jupiter and stop there, the picture looks less like an ambitious expedition and more like a multi-year game where any serious failure in the sequence of burns and flybys is fatal, and where there is almost no way to step off the ride once it starts. For robots, that is a risk we are willing to take. For people with current technology and realistic rockets, orbital mechanics is already telling you this destination is not for you. You're not riding to Jupiter, you're not a passenger, you are trying to keep a small closed ecosystem alive for almost a decade. And if that ecosystem fails, there is no emergency landing, there is no rescue, it just ends. Start with something very simple, what 4 humans actually need. A small crew eats, drinks, and breathes through tons of material every year. You need water for drinking, for food preparation, for hygiene. You need oxygen to breathe. You need food with enough calories and nutrients to keep people healthy under stress. On the International Space Station, a constant stream of cargo ships tops up all of this. For a Jupiter mission, there is no resupply. If you tried to pack 10 years of everything in a simple open-loop way, you're talking about tens of tons of consumables just for 4 people, before you add the mass of the habitat, the tanks, the engines, the fuel, the shielding. Now translate that into rockets. Today's heavy launch vehicles can put tens of tons into low Earth orbit, not hundreds or thousands in one go. So a ship that carries that much consumable mass would not be one launch, it would be many. You would be building the spacecraft piece by piece in orbit, docking modules, moving giant tanks around, wiring up life support systems in space. Every extra ton you add to keep the crew alive forces you to add more propellant to push that mass to Jupiter, which then forces you to add even more structure and more propellant to handle that, and the spiral grows. So you hit a wall, the logistics alone start to look unreasonable. And that raises the obvious question, can we get around this by recycling almost everything? Can we build a system that reuses water, air and nutrients so well that you hardly have to bring any extras? In theory, that is the way you would have to go. To make a decade-long mission to Jupiter even close to realistic, you need life support systems that recycle above 95 or even 99% of your water and air, and that recover nutrients from waste so you do not have to ship entire food stores from Earth. You want a closed loop, where what leaves the human body is processed, cleaned, and fed back into the system in another form. We already do some of this in orbit. The ISS recycles a lot of its water, including moisture from the air and even urine, and it can regenerate some oxygen from water. Those systems still need regular replacement parts, regular maintenance, and regular resupply from Earth. They also have not been run as a true, sealed, self-sufficient ecosystem for a decade straight. Nobody has yet flown a fully closed ecological life support system in space for many years. On Earth, there have been experiments with sealed habitats, and those showed how hard it is to keep the balance of gases, microbes, and nutrients stable, even when help is right outside the door. In deep space, if your closed loop starts drifting, if carbon dioxide builds up, if a key filter clogs and you do not have a spare, you cannot open a window. So for Jupiter, you are not just launching a ship, you are launching a biological and mechanical experiment that has to work with almost no margin for almost a decade. And even if you somehow manage that, you still have to deal with something that does not care about your recycling efficiency at all, the radiation slowly frying your ship and your crew the entire time. Here is the part that people often forget. The radiation problem does not begin at Jupiter, it starts as soon as you leave Earth's protective magnetic field and atmosphere. On the ISS, astronauts are still under partial protection from Earth, and even there, agencies track their lifetime radiation dose very carefully, limiting how long they can stay in orbit. Deep space is worse. You're exposed to galactic cosmic rays, high-energy particles coming from outside the solar system, and to bursts of particles from the sun, solar storms that can spike radiation levels in hours. For a Mars mission, you're exposed for maybe a year or two, including the journey and surface stay. For Jupiter, you're talking about years just travelling there and back, plus whatever time you spend operating in the outer system. The radiation dose is not a one-time hit, it's a drip that never stops. You can add shielding, and you must, but shielding is heavy, and heavy is exactly what makes the rocket equation angry, so you are forced into a trade, accept higher radiation doses over many years, with real cancer and organ damage risk, or accept a ship so heavy with protective material that launching and moving it becomes even closer to impossible. All of this is happening while the crew is isolated and under pressure, and that leads to another problem we have barely started to understand: what this does to human minds. Think about what you're asking of 4 or 6 people. You seal them in a metal volume not much bigger than a small apartment or a house. You cut them off from real-time speech with the rest of the human race, and you do that not for 6 months, but for many years. Every message from Earth is delayed by tens of minutes once you get far enough out. There is no live call with family, there is no quick talk with doctors, there is no immediate response from mission control if something breaks. The crew lives with constant background risk, constant awareness that outside the hull is vacuum, radiation, and millions of kilometers of nothing in every direction. We have data from ISS missions that last 6 months, sometimes a bit longer. We see mood changes, sleep issues, conflicts, stress. We train crews heavily to manage that, and we still work hard to support them from the ground. But we have never run a 10-year confinement test in deep space, with long communication delays, no physical resupply, and a mission that regularly reminds you, if this system fails, you die. When we talk about a Jupiter-class mission, we are guessing, we are stacking assumptions about human psychology and group dynamics without real data to back them up. That is not the kind of guess you want to make in one of the most hostile environments in the solar system. Put all of this together, and the picture changes. You're no longer thinking about a spaceship in the way you think about Apollo, or even a Mars transfer vehicle. By the time you add closed-loop life support, thick radiation shielding, structural redundancy, medical equipment, power systems, and enough living space to keep a crew functional for a decade, what you have built is basically a tiny world, a fragile artificial planet. It has its own water cycle, its own air cycle, its own food production and waste processing, its own psychological environment, its own internal climate. And that tiny world has to be launched piece by piece, assembled in orbit with 0 major mistakes, tested, and then sent into a region of space where radiation, distance, and gravity give you almost no forgiveness. The price tag in money, time, and risk is so high that when real space agencies compare it to simply sending robots, the answer is obvious. You do not gamble a miniature, human-filled world on a decade-long shot into the worst part of the solar system, not with the technology we have now, and not with what we realistically expect in the near future. If building and protecting that tiny world is already this hard just to make the trip, what happens when you finally reach Jupiter itself and you find out that the space around the planet is actively trying to destroy both the ship and the people inside it? The closer you get to Jupiter, the more space stops behaving like empty vacuum and starts acting like an invisible particle storm that can tear electronics apart and kill an unprotected human in shockingly short time. Jupiter has a huge magnetic field, far stronger and larger than Earth's. That field traps charged particles, mostly electrons and ions, and whips them around the planet at high speed, forming radiation belts. You can think of Earth's Van Allen belts as the small manageable version. Jupiter's belts are on a completely different level. The region filled with high-energy particles is estimated to be about 20,000 times larger in volume than Earth's belts, and the intensity in the worst zones is roughly 1,000 times higher than around Saturn. For a human body, that is not unhealthy or not ideal. That is a place where an unshielded person would reach lethal dose not in years, but in hours to days, depending on how deep they go. So, if the environment is that bad, how do we even send machines there? How do we get any science at all out of that region without everything just failing instantly? Look at how we design something like Europa Clipper. This is an uncrewed spacecraft. It has no blood, no DNA, no organs to protect, only metal and electronics. Even so, the design is extreme. Its electronic systems are selected and tested to survive total radiation doses on the order of 100 to 300 kilorad of ionizing radiation over the mission. That means parts, materials, and chips that are far more robust than what you find in normal satellites or consumer devices. On top of that, engineers plan complicated orbits that limit how long it spends inside the most intense zones. They add shielding around sensitive components. They schedule flybys and path choices to manage cumulative dose across years. And remember, this is all just to keep a robot alive, one that can be allowed to degrade slowly and eventually fail. There is no requirement that it still be functioning perfectly 10 years later. Once you realise how hard we have to work just to keep stainless steel and silicon functioning around Jupiter, the next question is obvious. What happens if you put living tissue into that same environment? For humans, we talk in different units, but the idea is simple. Space agencies track astronaut exposure in terms of sieverts and millisieverts, which map to how much risk of cancer and tissue damage you are adding. Lifetime career limits for astronauts are generally in the range of a few hundred millisieverts up to around a sievert, depending on agency rules and age. An acute dose of about a sievert in a short time already pushes cancer risk up significantly. Several sieverts in a short window can cause radiation sickness and can be fatal. Now put that next to Jupiter. In the inner parts of its belts, where many interesting moons orbit, unshielded instruments can accumulate doses that would be lethal for humans in hours to days. Even with some shielding, if you sit there for repeated orbits, the dose piles up fast. You do not have the luxury of just staying longer to finish work. Every minute in the wrong region is more damaged bone marrow, nervous tissue, and DNA. Over a multi-year mission, the cumulative dose from just cruising through the outer solar system is already a serious problem. Add repeated close passes inside Jupiter's radiation belts, and you are far beyond what we consider acceptable for human health. So you might ask, fine, then we just build better shielding, we wrap the crew in a thick protective shell, block the particles and keep them safe. But that is where the rocket equation hits you again. The most effective passive shielding for this kind of high-energy particle radiation is material rich in light elements, things like water or polyethylene. But to bring the dose down from lethal in days to tolerable over months or years, you're not talking about a thin layer. You are talking about tens of centimeters to meters of material surrounding the crew compartment. Wrap a modest living volume, enough for 4 people, in that kind of thickness, and you are suddenly dealing with tens to hundreds of tons of shielding mass alone. That is before life support hardware, structure, propulsion, fuel and everything else. All of that mass has to be launched out of Earth's gravity well. Then it has to be accelerated onto an interplanetary trajectory. Then at Jupiter you have to slow it down to enter orbit. And if you ever want the crew to come home, you have to accelerate it again to leave Jupiter and head back inward, then finally slow it down again near Earth. Because of how rockets work, the more mass you want to move, the more fuel you need, and the more fuel you add, the more structure and even more fuel you need to push that extra fuel. It is a loop that quickly becomes ridiculous. When you run the numbers, shielding at the level you would really want for humans around Jupiter does not just make the mission heavier, it makes it almost unlaunchable with any practical fleet of rockets. So instead of wrapping humans in a giant bunker, what do we actually do today to survive Jupiter's environment with robots? And what does that tell you? Take NASA's Juno spacecraft as an example. Juno does not sit in a low stable orbit the way a crewed craft around Earth or Mars might. It flies in a very elongated polar orbit. It comes in fast over one pole, dives near the planet for a short time to make its measurements, then swings far back out again, away from the worst radiation, before looping around for the next pass. On top of that, its most sensitive electronics are placed inside a heavy titanium vault, a compact box in the middle of the spacecraft that acts as an extra radiation shield. That strategy works for a robot because it does not mind spending most of its time far away. It does not need windows, does not care that its instruments are shut down during some passes to extend life. But a human mission to do something meaningful in the Jovian system would need more than quick dashes. You would want extended time near key moons, repeated low-altitude passes, continuous operations in regions where the belts are strong. You cannot just put the crew in a tiny vault with no view and no access to systems, and you cannot realistically keep them always far away from the most interesting areas. So you end up with a brutal mismatch. The places around Jupiter where the science is best are the same regions where radiation levels are most hostile to human biology. The work patterns that make sense for robots, short dives in and out, are barely enough for instruments, and nowhere near enough to justify risking human lives. When you put it all together, the environment around Jupiter is not just another challenge to engineer around. It is a hard boundary, a sign that says, with the materials and propulsion we have, machines can go here, humans cannot. And if just being near the planet, outside its clouds, is already this dangerous, what happens when you think about going deeper, into its gravity well and toward the planet itself? Escaping Earth's gravity is hard. You need a giant rocket, you burn through mountains of fuel, and everything has to work perfectly. Now imagine doing that not from Earth, but from a place where the gravity is so strong that Earth feels like the easy tutorial level. That is what Jupiter's gravity well really means. Start with the basic numbers, because they explain why this is not just harder, it is a different category. Jupiter is about 318 times more massive than Earth, and about 11 times wider. That means it is pulling on you with enormous force. If you go down into the top of its atmosphere, to the level where the pressure is about the same as sea level on Earth, the gravity there is roughly 2.5 times what you feel standing on the ground here. So instead of 1 G, you feel 2.5 G. That is more than double your normal weight all the time. For a human body, that is already tough. Your heart has to work harder, your blood is pulled down more strongly, moving, standing, even breathing, and a constant 2.5 G for long periods is not something we are used to. For a spacecraft, it is worse. Every kilogram of structure, propellant, life support, and cargo suddenly weighs more in that environment. Engines have to fight that pull the entire time they are thrusting. You do not just visit this gravity well, you sink into it, and the deeper you go, the harder it gets to climb back out. So the next question is, how fast do you actually have to go to escape that pull? Here is where the escape velocity number hits you. At the cloud tops, roughly where that 1 bar pressure level is, the speed you need to reach to break free from Jupiter's gravity and never fall back is about 60 kilometers per second. For comparison, Earth's escape velocity at sea level is about 11.2 kilometers per second, so Jupiter's is more than 5 times higher. That single number is not just trivia, it tells you how much kinetic energy your engines need to give your ship if you want to lift off from deep inside Jupiter's gravity and actually get away. Because energy goes up with the square of speed, if you need more than 5 times the speed, you need more than 25 times the energy per kilogram. That means, for the same type of rocket, you need insane amounts of propellant to push yourself to that speed, especially if you are starting from down in an atmosphere, fighting drag and high gravity the whole time. On Earth, a fully loaded multi-stage rocket is already almost all fuel by mass, with just a tiny fraction left over as payload. On Jupiter, to reach 60 kilometers per second from the cloud tops with chemical rockets, the math moves from hard to basically impossible. And that leads straight into the next point. What does that mean for any idea of landing people there and then getting them back out? If you imagine a human-rated craft descending into Jupiter's atmosphere slowing down, maybe floating or using some kind of wing or balloon system, at some point it is sitting inside that gravity well and that thick gas. To come back out, you need engines that can push that whole system to escape speed, plus enough extra to shape a trajectory that actually gets you somewhere useful. With the chemical propulsion we have, or even what we realistically expect in the near future, you simply do not get that kind of performance with a crewed vehicle. The thrust to weight, the fuel mass, the staging, it all goes beyond what we can build or launch. So any crewed vehicle that drops too deep into Jupiter's atmosphere is basically committed. It is not a lander. It is a one-way probe with people inside. You could maybe design something that survives for a while, drifting, falling slowly, sending back data as pressure and temperature climb, but there is no serious path where that vehicle lights its engines, climbs out of the gravity well, and flies home. The physics does not care how brave the astronauts are, it just tells you, once you drop in, you're not coming back. At this point you might say, fine, then we do not land, we just stay in orbit. Surely that saves us, right? Staying in orbit sounds safe, but look at what a low orbit around Jupiter actually means. To circle closely around a massive planet, you have to be moving very fast sideways to avoid falling in. That speed comes from the gravity well itself. You trade falling for orbital motion. Around Jupiter, even in a stable low orbit, you are still deep down in that gravity field. And to leave, you still need a big change in velocity. You still have to burn your engines hard for a long time to climb back out toward interplanetary space. We are not talking about a small correction, we are talking about tens of kilometers per second of delta V budget, depending on the exact orbit and destination. Now stack on top of that what we just talked about earlier. Those low orbits are parked right inside brutal radiation zones. So you have this nasty combination. You're sitting in a place where high energy particles are hitting you constantly, trying to damage your electronics and your DNA. And if you decide you have to leave quickly, the energy bill is enormous. You cannot just fire the engines for a bit and raise your orbit. The physics demands a huge amount of propellant. That makes the idea of a long-term low Jupiter orbit for humans very unattractive, not just because of radiation, but because you're locking yourself into a gravity trap that is incredibly expensive to escape. To really see how extreme Jupiter is, compare it with places we already understand better, the Moon and Mars. On the Moon, the escape velocity is at about 2.38 kilometers per second. On Mars, it is around 5 kilometers per second. We have already sent robotic landers to both, and in the case of the Moon, we have sent humans down and back. The rockets that launched from the lunar surface were small, tiny compared to Earth rockets, because the gravity and escape speed are low. On Mars, future ascent vehicles are bigger, but still in a realm we can at least imagine building and launching. Now put those numbers next to Jupiter's 60 kilometers per second at the cloud tops. The Moon, Mars, even Earth are in one class. You can design multi-stage chemical rockets. You can accept that most of the vehicle is fuel, and you can still get a useful payload off the surface. Jupiter is in a different class. Its gravity and required escape speed push you into a regime where traditional rockets have almost no room to work. For a robotic probe that just falls in and sends back data until it dies, fine, you do not need escape. For a human land and return scenario, it is basically off the table. So when people ask, why can't we just build a bigger rocket and go down into Jupiter and back? The answer is, it is not about willpower or bravery. It is about the shape of the gravity well itself. Once something with humans on board goes deep enough into that well and that atmosphere, with the propulsion technology we have, the universe quietly flips the sign on the mission from round trip to one way. You're not landing on Jupiter, there is no on to land on. The whole idea of touching down there is broken before you even think about rockets or fuel. We are used to planets like Earth and Mars, hard surfaces, rock, ice, maybe dust, somewhere for a lander's legs to actually sit. Jupiter is not that kind of object. It is mostly hydrogen and helium, the same basic stuff the Sun is made of. There is probably a dense core deep inside, some mix of heavier elements, but from space down through tens of thousands of kilometers, you are flying through fluid, not stepping toward a crust. The cloud tops you see in pictures are just the top of a thick, deep atmosphere, not a floor, not a platform. So that classic sci-fi image, the big ship descending, punching through some clouds, then gently hovering over a solid surface with mountains and plateaus, it just does not match the physics. There is no hidden continent under the colourful bands. As you go down, the gas gets denser, the distinction between air and liquid blurs, and you never find a place where a lander can deploy legs and say, okay, we are resting. And that raises the next question. If you cannot land, what actually happens if you try to go in? What does a dive into Jupiter really look like? We do not have to guess completely, because we already tried a small one-way test. In 1995, as part of NASA's Galileo mission, a dedicated probe was released to plunge into Jupiter's atmosphere. It had a heat shield, a strong pressure vessel, and instruments built to handle extreme conditions. When it hit the upper atmosphere, it survived entry, slowed down, and then fell for about 57 minutes, sending back data all the way. By the time it stopped transmitting, it had reached a pressure of around 22 bars, that is 22 times Earth's sea level pressure, and a temperature of roughly 150 degrees Celsius. Those conditions were enough to crush and overheat that small, hardened probe. It was simpler and tougher than any human habitat would be. No windows, no life support, no big internal empty spaces that could buckle, and it still did not make it very far compared to the full depth of Jupiter. A crew module, with habitable volume, fragile equipment, and a limit on how strong and heavy you can make the walls, would fail even sooner. So what killed the probe so fast? And why does it get worse so quickly as you go deeper? The problem is that in Jupiter's atmosphere, pressure and temperature do not increase slowly and gently, they ramp up fast. At the top of the clouds, you might be near 1 bar like Earth's surface, and the temperature can be extremely cold. As you fall, the gas above you gets thicker, the weight of the overlying atmosphere stacks up, pressure climbs past 10 bars, 20 bars, 100 bars and keeps going. At the same time, compression and internal heat drive the temperature from those cold values to hundreds, then to thousands of degrees. A human habitat is designed to keep 1 bar of air inside, while handling 1 bar outside may be a bit more. You build it like a strong can, but it is not meant to survive being squeezed by tens of bars of external pressure, while also being baked from the outside. Long before you ever approach anything like a solid region deep inside the planet, the hull would deform, seals would fail, materials would weaken, and the environment would go from dangerous to instantly fatal. So then people ask the obvious workaround: if you cannot go down, can you hang up high, can you float instead of fall? That is where the floating city or balloon habitat idea comes in. People imagine giant hydrogen or helium balloons, or lighter than air structures, parked in the upper atmosphere at altitudes where pressure and temperature are more like Earth. In theory, if the local gas is denser than what you fill your balloon with, you can float, just like an airship in our own sky. On paper, there are levels in Jupiter's atmosphere where something like that might be possible, at least for a while, but look at the full environment you would be living in. Even in those friendly layers, you are still inside a gigantic storm system, with jet streams, vortices, and vertical flows far stronger than what we see on Earth. Winds can reach very high speeds, directions change with altitude, turbulence can be extreme. You're also still sitting inside a powerful radiation environment, especially if your chosen height lines up with the orbits of some moons, or with field lines that direct particles through your region. And remember, if something goes wrong, your evacuation options are basically zero. You cannot easily climb to orbit, you cannot drop to a surface, you cannot ask another ship to come pick you up, because every rescue vehicle would face the same gravity, the same storms, the same radiation. So even if a floating habitat design is not impossible in pure engineering terms, it is sitting in a place where the margin for error is tiny. A tear in the envelope, a major system failure, a loss of buoyancy, and you either start sinking into higher pressure, hotter gas, or you drift into more violent weather or harsher radiation zones. There is no stable, safe, long-term platform here, just a constant fight against an environment that is more powerful than anything your structure can comfortably resist. And that leads to the core misunderstanding people have when they say land on Jupiter. On a rocky world, when you say reach the planet, you mean you descend through the atmosphere. You hit a surface, you touch down, you explore, you maybe take off again later. There is a clear difference between sky and ground. For Jupiter, reach the planet means you enter the top of a deep fluid envelope and you start falling and you keep falling, and the conditions get worse the deeper you go. There is no natural stopping point. There is no surface that behaves like the Moon or Mars. There is just denser gas, rising pressure, rising temperature, and eventually exotic states of matter near the core. So talking about landing on Jupiter is not just ambitious, it is using the wrong mental model. With our current propulsion and materials, sending anything with humans on board into the atmosphere is the same as agreeing that at some point the vehicle will be crushed, cooked, and chemically damaged until it no longer exists as a safe structure. You're not planning a visit to a surface, you're planning an extended descent into a region that does not want solid objects to survive. And if that is how the ground behaves, What do the storms in that same atmosphere look like for anything that tries to float or maneuver there? Imagine flying a blimp into a hurricane the size of Earth, and then finding out that compared to the rest of the planet, that hurricane is just one feature in a much bigger, more violent system. When you look at Jupiter, the most famous thing you see is that big red oval, the Great Red Spot. That is not a small storm, that is a storm larger than our entire planet, a massive rotating system with wind speeds that can reach hundreds of kilometers per hour. It has been going for centuries, maybe longer. We are not even sure when it started. On Earth, a hurricane lasts days or weeks before it breaks down. On Jupiter, you have a storm that just keeps going year after year, while new storms form, merge, and die all around it. And the red spot is not alone. The whole visible surface of Jupiter is bands of fast jet streams, swirling vortices, and convective storms that punch up and down through the atmosphere. Those clean band edges are not calm borders, they are regions where neighbouring jets are sliding past each other at high speed. That means sheer layers of gas moving in different directions or speeds, stacked on top of each other. So if you ask, what kind of weather does a floating habitat have to live in? The answer is not a local thunderstorm field, but a full planet wrapped in violent fluid motion from pole to pole. And that leads to the next question. What does that do to a structure that is trying to stay in one piece? Think about a human vehicle, maybe a balloon habitat or a large airship-type craft, trying to park in Jupiter's upper atmosphere. It is not sitting in a smooth, gentle flow. It is dealing with gusts, rapid shifts in wind speed and direction, vertical updrafts and downdrafts that can yank it up or throw it down. Those are not small bumps you get in an airliner. They are forces acting on a very large structure with wide surface area. As different parts of the craft sit in slightly different layers of wind, you get shear loads, parts of the ship pulled one way, other parts pulled another way. Over time, that constant stress beats on joints, anchors, cables, and hull materials. Even advanced composites and alloys have limits on how many load cycles they can survive before cracks start, before something snaps. Designing a vehicle to survive decades of that without access to a proper repair yard is not a normal engineering problem. It is a nightmare. You would have to overbuild everything, which adds mass, which makes the whole thing harder to float or maneuver. And remember, this is before we even talk about what is actually inside those clouds and what else the storms are doing besides just moving air around. So the next question is, what are those storms carrying that can attack the vehicle directly? Jupiter is not just wind and clouds, it is also one of the most intense lightning environments in the solar system. Observations show powerful lightning discharges deep in the atmosphere, bolts that can dwarf the biggest strikes we see on Earth. If you're flying a conductive structure through a region like that, you're not just dealing with pretty flashes in the distance, you're at real risk of direct hits, induced currents, and electromagnetic spikes that can fry electronics or damage systems. Now, add the chemistry. Those clouds are not pure water vapour. They include ammonia, water, and other compounds. Some of that can form droplets or crystals that are corrosive or reactive with certain materials. Over time, those chemicals can eat away at protective coatings, seals, and exposed metal. Then there are the particles themselves, tiny ice or ammonia crystals moving at storm speeds. When they slam into a structure at high relative velocities, they act like sandblasting grit, slowly eroding surfaces, windows, sensor covers, anything facing the wind. So the environment is attacking you mechanically, electrically, and chemically all at once. Given that, imagine what it is like to actually fly and navigate in this mess. Try to hold position. Try to stay at a safe level. On Earth, when you fly a plane or operate a blimp, you have charts, radar, satellite data, and a century of weather models. You know where jet streams usually sit, you know typical storm tracks. You still get surprises, but the system is mapped. On Jupiter, you're in a three-dimensional, constantly shifting fluid, with massive vertical flows and storm cells that can stack on top of each other. There are no mountains or coastlines to use as reference. Visibility can be low inside thick clouds. Instruments can be confused by turbulence, rapid changes in density, and electrical activity. Just holding a stable altitude becomes a constant battle. Updrafts try to throw you higher. Downdrafts try to pull you down into thicker, hotter layers. If you are using buoyancy, your lift changes as the gas around you changes temperature and composition, so you're always adjusting. If you use propulsion to stay in one place relative to some target, you're burning through propellant just to fight the winds. Navigation is not just point north, it is figure out where you are in a featureless moving medium that is changing under you in every direction. And all the while, you are trying to avoid zones of higher radiation, deeper pressure, and worse storms. So when people talk about atmospheric habitats on Jupiter, giant floating cities or research stations, it is not just that they would be difficult or risky. Look at how we operate here at home. Our airships and aircraft live in an atmosphere we have mapped and watched for a long time. We know the limits, we know what our materials can take. And even then, storms still wreck planes and balloons when they are pushed into the wrong conditions. On Jupiter, the whole planet's weather is powered not just by sunlight, but by strong internal heat and fast rotation. That combination feeds a global engine that never really calms down. Any human habitat inside that system would be betting lives against an environment we only understand in broad strokes from telescope images and a few probe measurements. We do not have fine-scale models of every storm, we do not have decades of local forecasts, and we cannot send a rescue fleet if something goes wrong. So storms do more than make the ride uncomfortable. They close the door on the idea that you can treat Jupiter's upper atmosphere like a place for stable long-term human platforms. If the winds and lightning already make the idea of living in the clouds look like a bad bet, what happens when you step back, away from the storms, and ask a different question? How do you even power a habitat or a ship that far from the sun, in a place where sunlight has become a weak distant source instead of the main energy supply? You're used to thinking of solar panels as almost free power. You point them at the sun and electricity just shows up. But by the time you're out at Jupiter, the sun isn't a blazing disk anymore. It's a bright star, and the energy you can pull from it drops to a weak trickle. Here's the basic problem. Sunlight gets weaker with distance very fast. At Earth's orbit, you get roughly 1,360 watts of solar power on every square meter facing the sun. That's the number our satellites and the ISS work with. Jupiter is about 5.2 times farther from the sun than Earth, and when you move that far out, the intensity doesn't just drop by 5, it drops by about 5 squared, so about 25 to 30 times weaker. Out there, you're down to something like 40 to 50 watts per square meter. To get the same electrical power you'd get near Earth, you need solar arrays that are tens of times larger in area. On a small robotic probe, you can actually do that. Look at NASA's Juno spacecraft. It carries 3 long wings of solar panels, each one stretching roughly 20 meters, forming a big 3-armed shape. Those arrays are huge compared to older deep space probes, and even then, Juno runs very carefully. It has to budget power. It doesn't have big heaters for humans, it doesn't run artificial gravity, it doesn't power a big propulsion system all the time. It's a lean, efficient robot that sleeps and wakes and throttles its instruments to stay inside a tight power envelope. Now try to scale that up in your head to something that can keep 4 or 6 people alive. You need power for air circulation, water recycling, CO2 scrubbers, computers, communication, lighting, cooking, exercise machines, medical gear, and that's just the life support side. Add electric pumps, valves, control systems, and maybe electric propulsion for fine maneuvers. To get that much energy from weak sunlight, you need solar wings far bigger than Juno's, maybe multiple giant trusses with panels deployed over a football field or more in total area. Those structures are not just bigger, they are more fragile and harder to protect. A micrometeoroid that pokes a hole in a panel near Earth is annoying but often manageable. At Jupiter, with long missions and no resupply, every hit slowly degrades your only power source. The panels also have to survive thermal cycling, radiation, and mechanical stress from any maneuver. So while solar is possible, it pushes you toward thin, wide structures that are exactly the kind of thing you would rather not depend on in a distant, harsh environment. That's why people say, fine, forget giant panels, why not use nuclear power instead? For missions to the outer solar system, engineers already lean on nuclear options, usually in the form of radioisotope thermoelectric generators, RTGs. These devices use the heat from decaying plutonium to generate electricity quietly and steadily for years. They're perfect for small robotic probes and rovers that need modest amounts of power and don't want huge solar panels. For something bigger, people talk about small fission reactors, compact nuclear power plants in space which could, on paper, generate kilowatts to megawatts of power if you design them well. But when you take that idea and plug it into a human habitat near Jupiter, the mass and complexity spike again. A safe reactor system is not just a core, it's shielding to protect the crew from neutron and gamma radiation, it's heat rejection systems, large radiators to dump waste heat into space, it's control hardware, backup systems and structure. All of that has a weight, and you're layering it on top of the already heavy radiation shielding and life support we talked about earlier. RTGs are simpler, but each one only produces a limited amount of power, so for a crewed mission you'd need several, plus redundancy, plus thermal management. You trade one problem, huge solar panels, for another problem, a dense, hot, heavy power plant you now have to launch, cool and protect. And while you're arguing about where the power should come from, you're also forgetting a quiet enemy that eats energy constantly, the cold. At roughly 5 astronomical units from the Sun, space around Jupiter is not just dark, it's cold. The equilibrium temperature out there, if you just put an object in sunlight and let it balance with the heat it radiates away, is somewhere around 110 Kelvin. That's about minus 163 degrees Celsius. Your spacecraft is radiating heat into that environment all the time. If you don't actively warm the inhabited areas, they'll drift toward those temperatures. On Earth orbit, keeping a module at room temperature is already a non-trivial thermal engineering job. You have sunlight heating one side and cold space sucking heat out the other side. At Jupiter, the incoming sunlight side is far weaker, but the radiative loss to space is still there, so you lean much more on internal heaters. Every watt you put into heating is another watt you have to generate from solar, nuclear, or some combination. Life support isn't just about air and water, it's also about keeping pipes from freezing, electronics from operating outside their temperature limits, and humans from dying of hypothermia. You end up using precious power just to fight the background tendency of everything to equilibrate to a deep freeze. So now stack all of this into one picture. Low solar flux forces huge panels if you want solar. Nuclear power brings along heavy reactors or multiple RTGs, thick shielding and big radiators. The cold environment forces extra heating and thermal control. The harsh radiation and long mission length push you toward more robust electronics and extra redundancy, which also cost power. If you want electric propulsion to help with fine control or station keeping, that draws even more. As your power budget grows, you add generation hardware, which adds mass. That mass demands more propulsion to move it, which raises your fuel needs. More fuel increases your structural requirements and your shield requirements, and very quickly you're back in the same rocket equation corner we've been hitting in every section. Even if nothing else about Jupiter were hostile, power alone becomes a serious bottleneck. You're trying to sustain a complex, hungry, human-rated system in a place where the main natural energy source, sunlight, has been dialed way down. This is why when mission planners sketch out crude outer-planet concepts and then start putting real numbers on power, mass and propulsion, the design often collapses. They find themselves adding and adding, trying to cover all the needs, and the ship grows into something that's more like a small space station fused to a nuclear plant than a practical vehicle you can actually launch. Jupiter doesn't just challenge your rockets and your shielding, it attacks your power budget from every direction. And if just keeping the lights on and the heaters running is this hard, what happens to the human side of the equation, when even talking to Earth turns from a live conversation into a slow, delayed exchange that stretches over almost an hour for every simple back and forth? At Jupiter, you don't call Houston, you send a message, you wait tens of minutes, and by the time an answer could possibly reach you, whatever crisis you were in is already over, one way or another. Radio signals move at the speed of light. That is the fastest anything can travel, and even that is painfully slow on these scales. Depending on where Earth and Jupiter are in their orbits, a signal from your ship to Earth takes roughly 35 to 50 minutes to arrive. The reply takes just as long coming back. So a simple back and forth, you ask a question. The answer can easily stretch past an hour, sometimes closer to 2. There is no live voice in your ear, no quick, try flipping this switch in the middle of a fault. Every time you ask for help, you are really asking your future self to handle something long after the moment has passed. Think about how that compares to the missions we usually imagine. Apollo crews around the moon had near real-time support. Mission control could watch their telemetry, spot issues, and talk them through checklists in seconds. Even crews on the ISS today operate with delays that are small enough you barely notice them in conversation. For Jupiter, that entire model breaks. If a valve sticks, if a fire starts, if someone is injured, by the time Earth even receives your first "we have a problem" call, you've already either fixed it or you have lost the fight. That means a crew out there cannot lean on ground control the way previous missions did. They need onboard navigation tools, onboard procedures, and onboard decision-making that can handle the full Hawks chain, from diagnosing a fault to executing a repair, with no real-time coaching. Checklists from Earth become suggestions you get later, not instructions you follow in the moment. You're not just far from home in distance, you're cut off from the whole support culture that human spaceflight has been built around. And that forces the next question. If you try to keep normal communication quality at that distance, what does that cost in hardware and power? The farther you are from Earth, the weaker your signal becomes by the time it reaches our antennas. It spreads out over a bigger and bigger sphere. To maintain high data rates at Jupiter's distance, you need a powerful transmitter, a big high-gain antenna on the spacecraft, and precise pointing so that narrow beam stays locked on Earth. On the ground, dishes in networks like NASA's Deep Space Network already operate near their limits for some deep space missions, juggling multiple spacecraft, adjusting schedules, and using advanced signal processing to pull weak signals out of noise. Now add a human mission that wants not just low-rate telemetry, but regular high-definition video, massive science data dumps, medical monitoring, and maybe constant habitat diagnostics. You're pushing bit rates up while distance is pushing signal strength down. To keep up, you either accept that communication will be slow, compressed, and sometimes interrupted, or you build extreme communication systems, which are heavier, more power-hungry, and more complex. Both options have real consequences. Either the crew flies with weaker connection to Earth, or the ship grows even bigger and more demanding just to talk. And while that is happening on the technical side, something deeper is happening on the human side, because delay changes how it feels to be part of the human world at all. On the ISS, astronauts can video call family and talk to controllers with delays that are basically like a normal call. Even on Mars, you are still in a regime where a short message takes seconds to maybe 20 minutes at the worst. It is slow, but in an emergency you can still send a description and get advice while the situation is evolving. From Jupiter, every conversation becomes a sequence of monologues. You record a message, you send it, you wait. Later, you get their recorded response. You are never in the same moment as anyone on Earth. That has psychological weight. You're already confined in a small space, already under stress, already living with risk. Add to that the feeling that nobody can be with you in real time. Not family, not friends, not doctors, not mission control. Over months and years, that is not just annoying, it can change how connected you feel, how motivated you are, how supported you feel when things go wrong. Your world shrinks down to the crew around you and the walls of the ship, and Earth becomes a distant, delayed presence, like a time-shifted signal instead of a living support system. So the question becomes, if Earth cannot be there with you moment by moment, can the ship itself take over that role? Can onboard systems handle the complexity that used to be distributed across thousands of people on the ground? Right now, the answer is not at the level you would want for a place as unforgiving as Jupiter space. We are just starting to field more autonomous spacecraft, ones that can handle some navigation, some fault detection, some reconfiguration on their own. Even then, most missions still lean heavily on teams on Earth, watching data, updating software, tweaking plans. Our habitats, like the ISS, also depend on constant ground support for planning, maintenance schedules, and emergency procedures. To send humans to Jupiter, you would need a completely different tier of autonomy. The ship would have to detect complex failures, isolate damage, reroute systems, and guide the crew through repairs with minimal help from Earth. Medical systems would need to support diagnosis and treatment far beyond basic first aid, because every serious condition would unfold long before a specialist on Earth could see it in real time. You would need onboard tools that can adapt when parts fail, when sensors break, when software behaves unexpectedly. In other words, you would need a level of self-managing, self-repairing habitat that we do not yet have, and you would be testing it for the first time in the worst possible place. So when people picture a human crew near Jupiter, they often imagine something like Apollo just sailed up, a brave team talking to mission control with a few extra seconds delay. The reality would be a handful of humans living inside a highly complex machine that has to manage most of its own problems, out of contact when it matters most, with Earth reduced to a slow, distant advisor. That is not exploration in the way we've done it so far. That is an experiment, not just in engineering, but in what human bodies and minds can take when you stretch time, distance, and isolation to their limits. And if you are already pushing your technology and your psychology this hard just to stay in touch, what happens when you finally ask the last uncomfortable question? Can the human body itself even survive years of this? In microgravity, under radiation, inside a closed loop? Or does biology become the final reason Jupiter stays off limits? Your body is tuned for one planet, one gravity, one radiation environment, Earth. A Jupiter mission asks that same body to survive almost everything it evolved not to handle for almost a decade with no way to step outside and recover. Start with gravity, or rather the lack of it. In microgravity, your muscles and bones are not holding you up anymore. Your body reads that as we don't need this much strength, and it starts to strip away what it thinks is extra. On the ISS, even with strict daily exercise, astronauts lose bone density and muscle mass. Their hearts and blood vessels adapt to a world where blood doesn't have to be pumped up against gravity the same way. 6 months in that environment is already a serious medical challenge. We track it, we study it, we worry about it. Now stretch that from months to years. A Jupiter-class mission means long cruise out, long cruise back, and maybe microgravity or low-gravity operations in between. You're talking about multiple years where your skeleton is unloading, your muscles are doing less real work, and your heart is beating in a very different context. Over that timeline, bone can become brittle, like someone with advanced osteoporosis. Fracture risk goes up. Cardiovascular changes can become harder to reverse. There are also eye problems we've already seen. Fluid shifts in microgravity can change pressure in the skull and around the eyes, leading to vision changes that sometimes don't fully go away. So the simple question is, if 6 months already pushes astronauts, what does 5 or 8 years do? And the honest answer is, we don't fully know, but the trend is not good. Then layer radiation on top of that. We already talked about the Jovian belts, but remember, even the cruise phase through deep space is not clean. You're outside Earth's magnetic shield for years, bathing in galactic cosmic rays and occasional solar particle events. Every particle that slams through your body can break DNA, damage cells, and plant the seeds for cancer later. Over time, chronic exposure also speeds up cataract formation in the eyes, and there are worrying hints that high doses might affect the central nervous system, potentially changing cognition or behaviour. Right now, agencies set career dose limits to keep long-term risk within what they consider acceptable. A Mars mission, with current shielding concepts, already starts to bump against those limits. A Jupiter mission, with more travel time and potentially harsher environments near the target, would stack even more dose on top, unless you add enormous amounts of shielding mass, which we've seen is very hard to launch and move. By the time a crew came home, if they came home, they could easily have taken multiple times the radiation dose we currently allow. You're not just accepting a higher cancer risk, you're almost guaranteeing significant health damage years or decades down the line. Now add a quieter, less obvious problem. What happens to your immune system and the microscopic life that shares the ship with you? Spaceflight messes with immunity. Some immune responses weaken, some become overactive. At the same time, the human microbiome, the collection of bacteria and other microbes living in and on you, shifts in weightlessness and enclosed environments. On the ISS, we've seen changes in which microbes dominate surfaces and air filters, and some bacteria become a bit more aggressive or resistant. In a sealed habitat over a decade, you are creating a small artificial ecosystem. New microbial communities can emerge in water systems, air ducts, food storage, even on walls. The crew carries their own microbiomes too, which evolve under stress, altered diet, and altered immunity. If a new nasty strain gains a foothold, or if someone's immune system gets weaker over time, infections could behave very differently than they do on Earth. And you can't just open all the doors, scrub everything, and bring in fresh outside air. You are stuck managing a tiny, self-contained biosphere with tools and knowledge that are still incomplete. So you might say, alright, maybe we don't keep people in zero-G the whole time, maybe we spin the ship, make artificial gravity, and at least fix the bone and muscle problem, but that sounds easier than it is. The basic idea is simple. Build a rotating structure, use centrifugal force to simulate gravity at the rim. But we haven't actually flown a large, crude rotating spacecraft, not even in Earth orbit. We don't have real data on how people handle years of living in a spinning habitat, with Coriolis effects that could make movement and fluids behave strangely. Engineering that kind of ship is also a mass and complexity bomb. You need a large radius to make the spin gentle enough that people don't get sick. Large radius means big structures, long trusses, or big connected modules. All of that has to be strong yet light enough to launch. Joints and bearings must survive years of rotation without service. If something goes wrong with the spin system in deep space, you can't easily repair or replace it. And remember, you still have to add radiation shielding, life support, power systems, propulsion, and everything else. This spinning section is on top of all the problems we already discussed, not instead of them. Put it all together and you see the pattern. A Mars mission is already at the edge of what we think human physiology can tolerate in terms of time away, radiation exposure, isolation, and microgravity effects. It is a stretch, but a stretch we can at least model and test in pieces. Jupiter pushes every one of those stressors to a much higher level. Longer microgravity or partial gravity exposure, higher accumulated radiation, longer communication delays, more isolation, more dependence on closed-loop systems and fragile ecosystems. At that point, you're not just talking about a risky mission, you're talking about something that, from a medical point of view, crosses into, we know this will probably harm the crew badly, and we don't have reliable ways to prevent it. That is why when doctors, radiation experts, and physiologists look at a crude Jupiter scenario today, the answer is not how soon, it's not with what we know now. The planet doesn't just challenge our rockets and our engineering, it hits our biology in ways that are slow, cumulative, and very hard to reverse. And if your ship and your crew are already this fragile, there's one more layer that pushes the whole idea over the edge. The simple fact that to even try this, you'd have to build something closer to a mobile fortress than a normal spacecraft, and we don't have the launch capacity or the budget to make that real. To keep you alive anywhere near Jupiter, your ship can't just be a sleek spacecraft. It has to be a moving bunker, a thick, heavy shell, built to survive an environment that wants to punch through everything you own. Start with radiation shielding, because that alone changes the whole design. When you look at the dose levels near Jupiter, especially in the regions where you'd want to operate for science, you quickly find that thin metal walls are useless for humans. High energy particles blow straight through aluminium and steel, and sometimes make things worse by creating secondary showers inside. To really cut that dose down to a level your body can tolerate over months or years, you want hydrogen-rich materials, things like water, polyethylene, or special plastics that slow and absorb charged particles more effectively. But you don't need a few millimeters, you need thickness. Rough estimates put it in the range of tens of centimeters to maybe a meter or more around the crew area if you want a serious reduction in dose. Wrap even a modest habitat, say something with the internal volume of a small house or ISS module cluster, in that kind of shielding and the mass skyrockets. You're quickly talking about tens to hundreds of tons just for the protective layer around the living space. That's on top of the structure that holds it, the tanks, the life support, the power systems, the engines. The safe room approach, where only a small region is heavily shielded, can help in solar storms, but around Jupiter, the environment is bad enough that the crew would basically have to live in that bunker zone all the time, which then needs to be large enough to actually function as a habitat. So you might ask, can we do something smarter than just piling on mass? Can we use fields instead of walls? Can we deflect particles with some kind of artificial magnetic shield? On paper, there are ideas. People study active shielding concepts, like using strong magnetic fields or plasma bubbles around a spacecraft to bend incoming charged particles away, similar to how Earth's magnetic field protects us. In simulations, some of these ideas look promising, at least for certain particle energies and mission profiles. They could, in theory, reduce how much physical shielding you need. But right now, these systems are experimental at best. We have not flown a full-scale active shield on a human spacecraft. We haven't proven that a manageable magnet or plasma arrangement can reliably protect a crew for years, through all conditions, without failing. You would be relying on high-power, complex hardware that must not switch off or degrade at the wrong moment. Betting a Jupiter crew's survival on that with no backups would be like jumping out of a plane with a parachute design nobody has actually used in a real drop. Until these technologies move from theory and lab tests to robust space-qualified hardware, they are not something you trust with human lives in the worst radiation zone in the solar system. Meanwhile, there's a mismatch you can't ignore, the difference between hardening electronics and protecting people. For something like Europa Clipper, you can test chips and circuits to handle total doses of 100 to 300 kilorads over the mission. You can put them behind metal vaults, you can accept that some instruments will degrade and eventually fail, and you plan the mission so you get your key data before too much damage accumulates. In other words, you push the hardware to its limits and write off the fact that it won't last forever. You can't do that with the human body. There is no rad-hard version of your cells. DNA repair mechanisms work up to a point, then errors accumulate. Tissues don't regenerate perfectly. The more dose you take, the higher your long-term cancer risk and the higher the chance of organ problems. Shielding that keeps electronics alive is nowhere near enough to keep you safe. If you dimension the ship so the hull and vaults are designed to the same standard as a robotic probe, you might save the computers and sacrifice the crew. To flip that, you have to add much more protection, which again means more mass, more volume, and more complicated structural design. Now think about the structure itself. Near Earth, when something big breaks, you have options. You can send a repair mission, you can dock a new module, you can swap components with spare parts nobody originally planned to use that way. ISS maintenance looks like a constant flow of hardware up and down the gravity well. At Jupiter, there is none of that. You get one shot. Whatever structure you launch and assemble before departure is what you live in for the entire mission. That forces you into a very conservative design philosophy. Every major component has to be built with redundancy, so that if one part fails, another can take over. Load paths through the structure need multiple backups so that a crack or impact doesn't cause a cascading collapse. Joints, hinges, and moving mechanisms have to survive years of thermal cycling and stress without fresh lubrication or replacement. You probably want in-situ repair capability, like robotic arms, internal 3D printers for certain parts, and modular designs that let the crew isolate and bypass damaged sections. All of that adds mass, adds complexity, and makes testing harder. You're not designing a sleek capsule, you're designing a long-life offshore platform, but in vacuum, under radiation, with no port to return to. When you add everything we've talked about so far into one mental picture, the habitat stops looking like the clean sci-fi ship you see in concept art and starts looking like a compact battle station. Thick radiation shielding wrapped around a core crew area, additional layers for micrometeoroid and debris protection, strong internal frames to handle loads from spinning sections if you add artificial gravity, redundant trusses and modules to survive impacts and failures, power systems, maybe nuclear, surrounded by their own shielding and radiators, all of it integrated with life support rings, storage and propulsion stages. The result is a vehicle with huge mass and complex geometry, something that can't be thrown into space on one rocket. You'd have to launch it in many pieces, assemble it in orbit over years, test it, and then, once it's proven, commit it on a one-off mission that ties up enormous resources. With current launchers and assembly methods, even building something like ISS was a massive international effort, and ISS still lives comfortably close to Earth, under partial protection and constant resupply. A true Jupiter-rated fortress ship would dwarf that challenge. So when you hear that sending humans to Jupiter would require a mobile bunker, it's not exaggeration. The planet and its environment force you toward a design that we simply don't know how to build, pay for, test and launch with the tools we have. Jupiter doesn't just ask for a better spacecraft, it demands an entirely new class of human space structure, and that alone is enough to push serious plans off the table. And if the ship you'd need already looks like a fortress that eats budgets for breakfast, the next obstacle is obvious. How do you even get something that big into orbit in the first place? And who is willing to sign off on a price tag that competes with everything else we want to do in space? Even if you somehow forced the physics to barely work, the price tag for a human mission to Jupiter would walk into the room and shut the whole idea down. Start with the first hard limit, just getting mass off Earth. Every kilogram of shielding, every kilogram of propellant, every piece of habitat, every power system, it all has to be pushed up into low Earth orbit before it can go anywhere else. Today's and near-future heavy lift rockets can throw tens of tons to orbit in a single launch, maybe up to around 100 tons if everything goes right with the biggest vehicles. That's impressive, but it's not magic. A Jupiter-class ship with serious radiation shielding, closed-loop life support, big power systems, propulsion stages, and structural redundancy very quickly ends up in the hundreds of tons, and if you're realistic about shielding and propellant, you can easily push into the 1,000-ton regime or more. That's not one launch, that's multiple, maybe dozens, each one expensive, each one a complex mission in its own right. Before you even think about leaving Earth's neighbourhood, you're staring at a huge stack of hardware that must be lofted piece by piece, with zero tolerance for losing a critical element. Getting the mass up is only the first step. The next brutal phase is building all of it into one functioning vehicle in orbit. Look at the record we have so far. The International Space Station took more than a decade to assemble, with dozens of shuttle flights and other launches, careful robotic arm work, spacewalks, and constant coordination between multiple space agencies. And at the end of all that, what you get is a station that orbits a few hundred kilometers above Earth, inside our magnetic field, with regular cargo visits and crew rotations. Now imagine something significantly larger and much more heavily shielded than ISS, with spinning sections for artificial gravity maybe, robust propulsion stages attached, and all the interfaces and fuel lines and structural links that implies. The assembly job jumps to a different level. You'd need new construction methods, more autonomous space tugs, possibly dedicated orbital shipyards, and safety protocols that we have not yet developed or tested. That's a whole new industry just to build one vehicle. And remember, after all that work, you then fire the engines once and send your one and only copy of this machine into an environment that might still kill it. So the obvious question every space agency asks is, why would you do that when you can already send robots to Jupiter for a tiny fraction of the cost? Flagship robotic missions are not cheap, but they are orders of magnitude cheaper than building and operating a human-rated fortress ship. For the price of designing, launching, and assembling a crewed expedition, you could likely fund a whole series of major robotic projects. Orbiters studying the planet's atmosphere and magnetosphere, probes diving into the upper clouds, landers or ice-penetrating missions on the moons, ocean probes for Europa or Enceladus-style environments, each one targeted, each one designed to handle extreme conditions without needing air, food, or psychological support. From a science point of view, that trade is obvious. Robots can already gather most of the data you'd want from the Jovian system, and they can do it without risking human lives. If one fails, it's a loss, but not a tragedy. If a human ship fails out there, it's a disaster on a completely different level. When real program managers look at the graphs, the choice isn't heroic humans versus boring robots. It's one ultra-risky crude stunt versus a fleet of robotic explorers mapping the system in detail. The second option wins almost every time. Then there's the question of risk appetite. Institutions that actually fund spaceflight, governments, coalitions, even private companies, tend to be cautious when human life is involved. They will tolerate some risk, but they expect a path where the mission is at least reasonably safe given the investment. A Jupiter mission stacks all the worst features together. Physics problems at the edge of what our rockets can do. Life support challenges we have never solved at this scale. Radiation environments that are lethal without insane shielding. Communication delays that break the support model we're used to. And then on top of that, a budget and timeline that blow past most other projects. Look at it from a decision-maker's seat. You are being asked to sign off on a program that will cost huge sums over decades, require new launchers, new assembly techniques, new habitats, new power systems, new medical approaches, and still carries a significant chance of killing the crew or failing outright. Meanwhile, you have Mars programs, lunar bases, commercial stations, and Earth-observing missions all competing for the same money and attention, many of which deliver clear benefits and are actually achievable. Saying yes to a crewed Jupiter mission is not just brave, it's reckless, and real people with real budgets generally do not go there. This is where budget starts to feel like its own form of physics. On paper, engineers can sketch extreme solutions to almost any technical problem. You can imagine absurdly large rockets, orbital factories, gigawatt reactors, multi-layered shield walls, and highly autonomous habitats. In principle, given infinite money and time, you can draw a path around most obstacles, but in the real world, in principle, doesn't cut contracts, and it doesn't buy launches. Every kilogram of shielding, every new piece of infrastructure, every extra layer of safety multiplies cost. And as the bill climbs, support falls off, public attention moves on, and the chance of a long-term stable commitment shrinks. At some point, the combination of price and risk doesn't just make the mission unlikely, it makes it effectively impossible. Not because the universe forbids it, but because the way our societies work means nobody is going to pay for a mission that dangerous, that expensive, and that scientifically redundant compared to robotic alternatives. So even before you hit the absolute physical walls, the economic wall rises in front of you. It says you can dream about sending humans to Jupiter, but you cannot build a real program around it. Not now. Not with the tools and priorities we actually have. And that's why when we do go to Jupiter, we go the only way that really makes sense. We send machines into harm's way instead of people. Here's the twist. We do go to Jupiter. We've been going there for decades. We just don't put bodies on board when we do it. Back in the 1970s, before we had any real idea how bad Jupiter's environment really was, we sent the first scouts, Pioneer 10 and 11, then Voyager 1 and 2. These were flyby missions, one-shot passes through the Jovian system. They mapped Jupiter's gravity field. They sampled its radiation belts. They took the first close images of its moons and storms. At the time, they were pure exploration, but in hindsight, they were also warning shots. Their instruments saw radiation levels far higher than what you'd ever want around humans. They revealed that Jupiter isn't just big and pretty, it's wrapped in an invisible minefield of charged particles. Those early trajectories were designed with hardware limits in mind, not human limits, and even then, the data told us, this system is hostile in a way you cannot handwave away. Then came Galileo, which took the next step, not just rushing past, but staying. It arrived in the 1990s after a long cruise and became the first orbiter of Jupiter. For about 8 years, it looped around the planet, flew by the major moons, and built a much more detailed picture of the Jovian system. It also carried that famous atmospheric probe. The probe slammed into Jupiter's atmosphere at enormous speed, survived entry, deployed its parachute, and then spent almost an hour falling through the upper layers, measuring pressure, temperature, winds, and composition. Then, as we already talked about, it died, crushed and overheated by the rising pressure and temperature. The orbiter itself took a beating too. Its electronics and instruments were not originally designed for the full radiation onslaught it faced, and over time the environment damaged systems, corrupted data, and ate away at its capabilities. By the end of the mission, Galileo was old, degraded, and still carrying something dangerous, Earth microbes on its surfaces. To avoid even a tiny chance of contaminating potentially habitable moons like Europa with our biology, Mission Control deliberately sent Galileo into Jupiter, commanding it to dive into the atmosphere and burn up. That ending says a lot. We crashed a robotic veteran into the planet to protect icy moons that we might someday explore more carefully. We never even considered bringing it home. Around Jupiter, robots are expendable, and that's exactly how we use them. After Galileo, we built a mission that leaned into the radiation problem directly, Juno. Juno doesn't sit in a low equatorial orbit, it flies in a highly elliptical polar orbit. It swings in over a pole, dives close to the planet for a short, intense science pass, then shoots far back out, away from the worst of the belts, before coming in again. Its instruments are focused on Jupiter's interior structure, gravity and magnetic field, trying to answer questions about how it formed and what's happening under those clouds. To survive, Juno packs its most sensitive electronics inside a titanium vault, a thick box that acts as armour against radiation. Its orbit is tuned to balance science return against cumulative damage. Some instruments are powered down during the riskiest parts of each pass to extend their life. Even with all that, the mission timeline is finite because we know the radiation will eventually win. Look at that profile and ask yourself, do you want humans living inside a ship that has to do those same close dives repeatedly in those same regions, accepting that every pass eats into their safety margin? Juno's survival strategy is exactly the kind of contortion you do not want to impose on a crew that needs constant stability and safety. Now we're moving into the next wave, missions focused less on Jupiter itself and more on its moons, which may hide subsurface oceans. NASA's Europa Clipper and ESA's JUICE mission are built to do repeated flybys and detailed studies of moons like Europa, Ganymede, and Callisto. They will sample thin atmospheres, map ice shells, study magnetic signatures that hint at salty oceans under the crust, and search for conditions that might support life. Their trajectories and hardware are designed again to balance scientific ambition with radiation survival. They dip in, collect data and get out, carefully managing how much time they spend near Jupiter's worst zones. These missions point straight at the real path forward. If you want to explore the Jovian system deeply, you send machines over and over. You evolve your electronics, your shielding, your software, and your instruments. You risk hardware, not people. Each probe can be tailored to a specific task. Radar mapping of ice, ocean sensing, plume sampling, high-resolution imaging. Humans, meanwhile, stay where the environment is, at least somewhat compatible with our biology, closer to Earth, or maybe one day on safer moons or in high, protected orbits far from the belts. The division of labour is clear. Machines go into the hellscape, humans watch from safer ground. And here's the key point that often gets missed. Every new mission to Jupiter doesn't make a crewed mission seem more plausible, it does the opposite. Pioneer and Voyager showed intense radiation and huge distances. Galileo revealed just how harsh the atmosphere is, and how badly long-term radiation damages hardware. Juno mapped a magnetic and radiation environment that's even more complex and vicious than we thought. Each upgrade in data has brought more surprises, more layers of complexity, and more reasons to respect just how extreme this system is. Instead of gradually ticking boxes on the road to humans next, the data keeps underlining the same conclusion. Jupiter is a place where robots thrive and humans don't belong. It's not that we're afraid to go, it's that the rational cost-benefit calculation never lines up. You get more science, more safely for less money by sending machines. You get enormous risk, huge expense and long-term damage to any crew you send for relatively little extra scientific gain. So when you look honestly at what we've actually done at Jupiter, the pattern is obvious. We already treat it as a robot-only zone. We build tougher probes, smarter instruments, better shields, and we accept that some of them will die early. That's fine, that's the right way to explore a system this hostile. And that brings you to the last big question people always ask. Could some future technology, some new kind of engine or shield ever change that? Or is no humans at Jupiter baked into our story for good? Okay, you say, what if we invent crazy new engines? What if we stop thinking in terms of today's rockets and jump to nuclear and beyond? Does Jupiter suddenly become fair game then? Let's start with upgrades that are at least on the edge of reality: nuclear thermal and nuclear electric propulsion. A nuclear thermal rocket is basically a reactor heating propellant, usually hydrogen, and throwing it out the back. Because the reactor can run hotter than a chemical flame, you get better efficiency, roughly double the specific impulse compared to the best chemical rockets. Nuclear electric systems go a different way. They use a reactor to generate electricity, then power high-efficiency electric thrusters, which use less propellant over time, but at very low thrust. Both ideas help with one big issue: propellant mass. If you can get more push per kilogram of fuel, you can shrink your tanks, cut down on staging, and maybe shorten the trip. For a Jupiter mission, that could mean fewer years in transit, less time soaking up deep space radiation, and a smaller total vehicle mass. That sounds good, and on paper, these systems move some numbers in the right direction, but look at what they don't touch. They don't change how strong Jupiter's gravity is. They don't make its radiation belts weaker. They don't conjure a solid surface where none exists. You still have to shield the crew, you still have to handle communications delays, you still have to deal with the gravity well if you go too deep. Faster travel helps, but it doesn't flip hostile into friendly. So then people push further out and say, fine, what about fusion drives or giant laser arrays back home, pushing light sails or other beamed power ideas? Could those finally break the problem open? In theory, yes, far future propulsion concepts like fusion engines could give you extremely high exhaust velocities, meaning you get huge delta V without ridiculous amounts of propellant. Beamed power could let you accelerate a spacecraft without it carrying the energy source, which sounds perfect for long voyages. In that world, you can imagine transit times to the outer solar system dropping from many years to maybe months or less. But right now, that is all could and in theory. We don't have a working fusion propulsion system. We don't have real beamed energy infrastructure in space that can deliver controlled, continuous power over billions of kilometers. Every one of these concepts drags its own massive engineering and safety questions behind it. How do you confine fusion plasma reliably on a moving ship? How do you aim a beam over astronomical distances without missing, or without damaging things in the beam's path? How do you handle waste heat from powerful reactors in the cold of deep space? None of this is simple, and none of it removes Jupiter's basic environmental threats. Even if you could fly there faster, you still have to live there or nearby under those same brutal constraints. So maybe the smarter move is not to brute force the whole mission from Earth, but to use local materials instead. You picture building a base on a Jovian moon like Callisto, mining ice and rock, and using that mass as shielding and structure. Now that idea actually has some potential. A moon like Callisto sits far enough from Jupiter that the radiation environment is milder than, say, Europa's. If you dig in, build habitats under several meters of ice or rock, you can get good radiation protection without lifting all that shielding out of Earth's gravity well. That could, in a far future scenario, give you a safer outpost in the outer solar system, supplied by slower cargo traffic and maybe serving as a staging point for robotic missions deeper into the system. But notice what even that future doesn't fix. Living on a shielded moon base near Jupiter is not the same as popping down into Jupiter's atmosphere. All the gravity, pressure, storm and radiation belt problems we talked about still wait for you the moment you try to go down toward the planet. Your outpost might be a good place to control robots, process data, refuel probes, maybe even build new hardware, but any crude dive into the Jovian atmosphere is still suicidal with anything close to our current or near future technology. A safer base near the giant is still near, not on, and that distinction matters. Then there's the idea that advanced AI and smart self-repairing structures could change the game. If you had habitats that can monitor themselves in real time, detect microcracks, reroute power, heal damaged circuits, and manage life support dynamically, you ease the burden on the crew and reduce the need for constant advice from Earth. Pair that with robotic maintenance system that can swap modules, print replacement parts and patch up damage, and life in deep space gets more manageable. The communications delay hurts less if the ship itself can act like a full-time expert engineer and doctor. And yes, that would help. Smarter habitats would make operations more efficient, reduce the chance of small problems snowballing into disasters, and let humans survive in tougher places than they could with today's dumb hardware. But again, look at what AI can't change. It doesn't weaken Jupiter's gravity, it doesn't reduce radiation levels, it doesn't make thick shielding lighter, it doesn't suddenly allow our bones to ignore microgravity, it improves how we manage logistics and failures, it doesn't rewrite the underlying environment. If you build a nightmare mission with impossible margins and say AI will fix it, you're not solving the problem, you're just moving the gamble from human judgment to software and hoping nothing unexpected happens. So when we say impossible for a human Jupiter mission, we're not saying no one in the universe could ever do this. Maybe a civilization with technology far beyond ours, with materials we don't have, with power systems we can barely imagine, could engineer some insane solution. They might build enormous shielded arcs, or warp the rules with physics we haven't discovered yet. For them, maybe Jupiter is a harder target, but not a forbidden one. For us though, for the next many generations, the picture is much simpler. Distance, radiation, gravity, lack of a surface, cold, communication delays, biology, power, cost, all stacked together. You can nudge one or two pieces with better engines or smarter software, but the whole tower of constraints stays standing. With anything like our current tech base, or even a few reasonable steps beyond it, Jupiter stays on the no humans allowed side of the line. We explore it with machines, we might someday live on its safer moons, but we don't drop people into its shadow and pretend that we can bring them home safely. And that brings you to the real conclusion, the uncomfortable but important one. Jupiter is not just another destination we haven't reached yet, it's a boundary marker, a place in our own solar system that tells us, very clearly, where human spaceflight stops and pure robotic exploration takes over. When you add everything up and you stop thinking in pieces and look at the whole picture, Jupiter stops being just another place we haven't reached yet and turns into something else. It becomes a hard boundary on what human spaceflight can actually do with anything like our current technology. Look at how the barriers stack, one on top of another. First, distance. You're not talking about a long trip, you're talking about journeys that, with realistic propulsion, eat up the better part of a decade, round trip. That instantly multiplies every problem with life support, hardware reliability and crew health. Then orbital mechanics step in and lock you to narrow launch windows and long, delicate transfer paths. You don't choose when to go or when to come back. The positions of Earth and Jupiter make that decision for you. And if you miss your shot, the energy and time costs explode. On top of that, the environment itself starts to look like a stacked weapon. Radiation belts that are far beyond anything near Earth, powerful enough to destroy unshielded electronics and deliver lethal doses to humans in hours or days. A gravity well so deep that escape speeds at the cloud tops are more than 5 times Earth's, making any land and return mission essentially impossible with chemical rocketry. An atmosphere with no solid surface, just an endless downward gradient of rising pressure and temperature that turns any deep descent into a one-way trip. Global storms, lightning and turbulence that are not just a weather pattern, but a structural threat to any vehicle that tries to float or fly there. Each of these could be a showstopper on its own, Together they don't just make things harder, they push the whole concept into this isn't a human environment full stop. So what does Jupiter actually teach you about exploration, besides the fact that the universe can be brutal? It forces you to accept that not every interesting place is meant for boots on the ground. We grew up with a simple story: humans explore, we plant flags, we walk on surfaces. The moon fits that story. Mars sort of fits that story if we push our tech hard enough. Jupiter breaks it. Here, the scientifically smart and honestly ethically responsible move is to send machines in first, second, and maybe forever. You let robots dive through radiation belts, skim cloud tops, and sample hostile moons. You let them get cooked, fried, and torn up by an environment that does not care about human dreams. You keep the living explorers where nature is only kind of trying to kill them, not going all in. That might mean lunar bases, Mars outposts, free-flying stations in cislunar space, or one day, habitats in the asteroid belt. Places where the risks are real, but can be pushed down to something rational. Jupiter's value, in a way, is that it forces you to draw a line and say, this is where the role of robots and the role of humans split. If humans ever do get close to Jupiter in a serious way, the smart money is not on cloud cities or landers diving into the atmosphere. It's on the moons and on carefully chosen orbits. A base on a relatively safer outer moon like Callisto, buried under meters of ice or rock for shielding, could one day be a thing you can at least talk about without leaving reality. Highly inclined orbits far outside the worst of the radiation belts might hold future relay stations or research platforms. These concepts are still extremely ambitious and would take tech and infrastructure well beyond what we have now, but they are orders of magnitude less suicidal than pointing a crewed ship at the planet and trying to go down for a look. And that brings you to the story you actually tell the viewer at the end, the part that sticks. We don't stay away from Jupiter because we are cowards. We stay away because, when you do the math honestly, the universe simply wins that round. The combination of distance, orbital mechanics, radiation, gravity, storms, lack of a surface, power and communication limits, biology, structure and cost, all pile up on one side of the scale. On the other side, the benefit of sending actual human bodies there instead of machines is small. The balance is brutal and clear, so the real punchline is simple, and it's the line you leave them with. We don't go to Jupiter because the universe won that round. And in accepting that, we actually learn something important. We learn where human exploration can realistically reach, where robots should take over, and how the solar system quietly sets rules for us, even if we don't like them. Some worlds you walk on, some worlds you orbit, and some worlds, like Jupiter, you only ever see through the eyes of your machines, because that's the only way you get to see them at all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.